pi in college and the last in fiber.
It's technically correct. It's technically correct.
That's a big bonus.
Are you okay? Anybody watch the lecture videos recently? No. I was just wondering how the audio is coming out. Okay, well, let's finish 12.1. We were looking at the example, x is sine 2t and y is 2 sine of t. And we wanted to find the points where we had a horizontal and a vertical tangent. We did compute the derivative dy over dt divided by dx over dt. We've got a horizontal tangent when the numerator dy over dt is 0 and the denominator is not 0. So we have our derivative here, horizontal tangent when cosine is 0 at pi over 2 and 3 pi over 2. So once we have those t values, we plug back into the original equation to obtain the points 0, 2, and 0, negative 2 on the curve where we have a horizontal two horizontal tangents. I'm going to go ahead and put the graph in our notes so we can kind of reference that. And then we can see that the work we've done here justifies the horizontal tangent on the top and the horizontal tangent on the bottom. Does anyone have any questions on what we've done so far? So then we'll look at the vertical tangents. Our derivative was cosine t over cosine 2t. So we've got vertical tangents when the denominator of our derivative is 0. Is it? Let me go back up here. Cosine 2t is equal to 0. And we're keeping in mind, and the numerator cannot be 0. We already know that the numerator is 0 at pi over 2 and 3 pi over 2. We're just going to try to keep that in mind when we say the zeros of the denominator. If we get like pi over 2 or 3 pi over 2 as well, then we've got to take a different approach. So when is the cosine of 2t equal to 0? Yeah. When t is pi over 4. What else? Remember, this thing goes from 0 to pi over 2 as the domain. Yeah, 3 pi over 4. What else? Do you want to make sure these t values are in our domain? So maybe the way you're thinking about this is we know the cosine of the argument is 0. So let's think of it this way. Cosine of 2t is 0. That's the same thing as asking when does the cosine of theta equal 0, when theta equals 2 pi over 2 and 3 pi over 2.
When cosine of theta.
Oh, 0, yeah. Sorry, I said 0, but I wrote. And normally, if that's what we were solving like we did in the first part of the problem, we would stop because we say, well, any other value as outside of pi over 2. But we got to think that since we're looking for when 2t is equal to 0, the argument of cosine, that we do want to go out more here because when we look at the double angle, it's actually going to be half of these. right? Oops, sorry. We would go to, we're going outside of 2 pi because now we're gonna go, since we're doubling that, we're gonna think about going out to 4 pi. So then our theta is just 2t, we just multiply by a half. So you should come up with 4 values here for t at which you have a vertical tangent. Everybody all right with that? And I mean, if we use the figure provided as a reference, you see that makes sense because here at all of these points on the edges, we have our vertical tangents. So now we just need to see what points those actually are. And we're plugging that back into the original x sine of 2t. Y is 2 sine of t. We're going to do that for all 4. So once we plug back into the original, that's going to give us our 4 points where we have our vertical tangent. So with pi over 4, we get 1 column root 2. 3 pi over 4, 1 negative root 2. 5 pi over 4, negative 1 root 2. And 7 pi over 4, negative 1, negative root 2. It's vertical tangents. And those were the 4 points that we identified in green on the graph. Does anyone have any questions on that? This is a theme that shows up again when we start looking at polar coordinates. If we got a graph in polar coordinates, how do we determine where the tangent lines are vertical and horizontal? So it is something we see again.
So what direction is it unfolding? Is it going from the pi over 4 value to 3 pi over 4 value?
So yeah, what direction is it? What's the positive orientation? Is it kind of looping around like this? Is it starting here and looping around like that? Really, in order to see that, we would have to plot. We could plot that, or you could just pick some t values. Initial point when t equals 0, terminal point when t equals 2 pi, and sort of, look at the dots and which way they're kind of moving around. But just looking at the static image, there's no way for us to tell that. Looks like it's going on. And it does bring up a sort of this point of contention when we look at other coordinate systems. Even in like three-dimensional space, there's issues, right? Because if you're looking at a two-lane highway from afar, you can see two cars coming at each other and then passing, but to the eye, it looks like they're going to collide or intersect. We know if we shift that perspective like this, then we can see that they're not actually going to intersect. So, sometimes these, if there's two curves and we're trying to figure out where do they intersect, they might not intersect at the same, quote unquote time, right? Like this graph may hit this point at some certain time, and another graph may come through the very same point at a completely different time. So we run into that issue in the polar coordinates too. Generally, when we're finding more advanced things like this, a figure is provided. So we can utilize symmetry in the figure, or you can use the figure to sort of guide your decision making. Because a lot of times, like solving analytically where two things intersect isn't going to give you all of the intersection points. And then so we can look at a graph to do that. It's not preferable to look at a graph because what if you messed up graphing? So it brings up another issue of in certain kind of coordinate systems, how do we find points of intersection? It's not as straightforward as like finding them in Cartesian coordinate system. Okay, we've got one more topic with parametric equations, and that is of the arc length. Skip the derivation of this, but the arc length in parametric form is defined as the integral from a to b, square root of f prime of t squared plus g prime of t squared, where f prime of t is x prime with respect to t, and g prime of t is y prime with respect to t. So if you want to think of that as the square root of x prime squared plus y prime squared with respect to t, you certainly can do so. So we have find the arc length of the asteroid defined as follows. So we'll go ahead and put that figure in here too. That's what we're going to find the arc length of. And with the figure provided, I think it's easier to use symmetry instead of trying to find the arc length of the entire thing. Just find the arc length of one piece and multiply that by 4. Yeah. No, I just went out far enough that I would get the whole thing. Yeah. Now, these problems will say, in order to find the arc length, you've got to make sure a complete curve is generated. I wouldn't worry about that. The problems that you are given, a complete curve is generated on the interval. So we've got a complete curve generated from 0 to 2 pi.
If we didn't have any graph, we should solve it. Right? We don't need to worry about it.
Yeah. Yeah, and then really so we could, if we were just given this without the graph, it would probably say something like, assume that a full revolution is made between 0 and 2 pi or something like that. Okay. Or you were saying something else.
I mean, would it matter? I mean, we would just plug and chug with what we got, right?
Yeah.
We need to analyze it.
Right, yeah. Okay, So we need to find x prime and y prime and then square them. Add them together, take their square root. So it doesn't matter how you do all that. We can do all that individually if we want to. But x prime or f prime, derivative of cosine cubed, so that's 3 cosine squared times negative sine. And y prime, 3 sine squared times cosine. Yeah, so when we square it, since it's just a product, we'll just square all of them. So we have negative 3 squared, cosine squared, squared, and sine squared. Y prime squared, 9 sine to the 4th cosine squared. So we can either put this all in the integral from this to this under the radical, or we can take the square root and try to simplify that first. So there's x prime, square root of x prime squared plus y prime squared. Okay, so ideas on how to simplify that.
Pull out a 3.
Okay, so we get it. Yeah, factor of 9 comes out, so we have 3 times radical. Pull out a, what now? Yeah, so greatest common factor, we get a cosine to the 4th, sine squared, sine to the 4th, cosine squared, my bad, it's cosine squared. So it looks like we can take out a cosine squared from each term and a sine squared from each term. We're going to take that, our common factor out, cosine squared t, sine squared t. And then that leaves us with cosine squared t sine plus sine squared t. Equals 1. The product doesn't equal 1. The sum does equal 1 though.
Oh, those are multiplied.
Yeah. Okay, so we just have 3 times the square root of cosine squared t times sine squared t. Okay, yeah, so this is where we have to be careful. If we say that we're going to integrate from 0 to 2 pi, and we have the square root of a quantity squared. So let's look at this, the square root of x squared. What is that equal to? It's not x, it's not plus or minus x. What if my claim is that this is x, what if I take the square root of 2 squared? Then this formula would say that that's equal to x. But the formula would also say the square root of negative 2 squared equals negative 2. Absolute value. So we've got 2 choices at this point to move forward. Let me just write them down. But the idea is, if I don't know if that quantity under the radical being squared is positive or negative, if it has the tendency to be both, depending on where it's at, then I have to look at the absolute value of that to ensure, this thing doesn't happen. So if I say, all right, well, here's my integrand, and I'm gonna go from 0 to 2 pi on that thing.
We pull that 3 out front there.
Yeah, I'm gonna pull that 3 out front. So if I just look at it like that, and I said, okay, well, that's equal to the integral from 0 to 2 pi of just cosine t times sine t, that's not correct, because from 0 to 2 pi, cosine and sine are both positive and negative. So yeah, then you have to deal with partitioning up sine and cosine. Do you know what the graph of sine cosine looks like and where it's positive and where it's negative? To split that up. It's not as straightforward. Like if we knew, like when we looked at what was it, displacement versus distance traveled, and we had a graph that was like this, say like that, and we knew this was 5, 4, 2, and 0. Right, then to look at the absolute value on this function, if we integrate this, we had to say that we split this up. The ones that are positive are fine. I can go from 0 to 2 on the function, and from 4 to 5 on the function. But the ones that were negative, I had to put a negative in front of them, right? And go from 2 to 4, and whatever. So let's say that's 5 to 6. And then negative integral from 5 to 6, right? I remember doing that. I don't know. Maybe you know what cosine times sine's graph looks like. I'm not familiar with that off the top of my head. Let's see. I think that's it. Yeah. And then we're sort of so these two from 3 pi over 2 to 2 pi, we have to make that integral negative, and from pi over 2 to pi, we have to make negative. These two above, we would leave alone.
How
But
would you know that though? How would you figure that out?
yeah, exactly. Then you would have to like plot points, try to generate the graph, right? It's really tedious. So instead of doing that, let's go back up to the figure and say, well, if I take 4 times this length right here, then I have the entire thing. And so how does that help? So let's write, or we can say it's 4 times the integral from where to where. If I'm just looking at that one piece, 0 to pi over 2. So if I look at this thing from 0 to pi over 2 and then multiply it by 4, I'm still getting the total length. Except the advantage of looking at the integral from 0 to pi over 2, both sine and cosine are positive from 0 to pi over 2. So we don't need to worry about the absolute value here.
Yes, how would you know that you multiply by 4 without looking at the graph? Test.
On a test, I would give you the graph. So I don't expect you to graph these really complicated figures, like lines and circles. Those things should be pretty standard, but like these kinds of things, we could figure out what the graph looks like, but you have to plot a whole lot of points. It's super long and tedious to do that. Yeah, right. Okay. So let's write it out like this. We have 12 times the integral from 0 to pi over 2 cosine t times sine t dt. We'll write here since cosine of t larger than or equal to 0 and sine of t larger than or equal to 0 when t is in between 0 and pi over 2. So we don't need absolute value there. Okay, so how do we integrate? U substitution. U is sine, du cosine. So we've got 12 times the integral of u du. We might as well change our bounds since we're dealing with u. It would be easier. If t is equal to 0, u is equal to the sine of 0, which is 0. And if t is equal to pi over 2, u is equal to sine of pi over 2, which is 1. Pretty straightforward integral there. So we've got u squared over 2, 6u squared from 0 to 1 gives us 6. So the length of that curve is 6. Do you have any questions on this example? So honestly, with these kinds and then with polar, as we'll talk about in the next 2 sections, utilizing the graph is often very helpful. Otherwise, they're really tedious. So you might remember a little bit about polar coordinates from like a trig or a pre-calc class. So the idea of the coordinate systems that are represented by polar coordinates is the same idea when we look at like the rectangular or the Cartesian coordinate system. Any point, let's say our point is, let's say we've got a point that's 4, 4 in rectangular coordinate system. So the way we describe those, of course, how far we go left or right, and then how far we go up or down. But we can also think about that point being described by a distance from the origin, which we're going to call r, and how far from the positive x-axis we had to rotate to get to it. And we're going to think about that as theta. So any point that we can represent in rectangular or Cartesian coordinate systems, you can also represent by describing a distance from the origin and an angle of rotation. And then those give us our polar coordinates, r theta.
So they kind of get like nautical miles.
I don't know. Maybe. But the advantage of polar coordinates is that, you know, especially when you're trying to describe like circular paths or objects, you've got, it's a little bit easier to work with because you're already in sort of this circular coordinate system. So this is a typical rectangular graph paper, and this would be a graph paper for polar coordinates, which they still do make. Desmos has that ability too. You just go up here to settings. You can switch the grid from rectangular to polar. So we'll look at that in a minute, but here's our theta equals to 0. There's pi over 6, pi over 4, etc. Just like the unit circle. The point at the origin is, in polar coordinates, is called the pole. And our positive x-axis is called the polar axis. And so what we'll see is that if I can describe any point in the plane by distance from the origin and a rotation, then I can also perform all of the other operations on those kinds of things that we can in Cartesian coordinate systems. We can take derivatives, we can find areas, we can find arc lengths, all of that stuff. Yeah, this right here. Yeah, so it's like this piece right here is the polar. So the thing with rectangular coordinates is we had a unique representation for any point. If I said that that's the point 44, you know exactly where it's at. But you can think that just because here theta repeats 2 pi, right? But there is not a unique representation for any point in polar. In fact, there's infinitely many representations for polar coordinates. So why is that? So we haven't quite talked about this, but each concentric circle here is for measuring the radius. So like if I go out this way, right here, that's r equals 1, this is r equals 2, this is r equals 3, and so forth. So what if I said I had the point, 4, 0? Radius 4, angle of rotation is 0. What's another point with a different representation that describes the same point? Yeah, 4, 2 pi is also the same point. Also 4, negative 2 pi is the same point. So over here with rectangular coordinate systems, there's a unique representation for each point. I mean, yeah, we could say 8 over 2, comma 8 over 2. It looks different, right? But we know 8 over 2 is 4, comma 4. When we see these things, 4, comma 2 pi, 4, comma 0, yeah, they are the same point. But there's in terms of simplifying numbers, there's nothing else to do there, right? Which kind of is one of the main problems. Finding points of intersection isn't that easy because maybe one curve crosses here at 4, 0 and the other curve crosses at 4, comma 2 pi. So they're sort of, even though they're crossing the same point, if you set them equal to 0 or each other or whatever, then you may not actually come up with the other representations for those. So let's just note that here, not a unique representation.
So each Cartesian coordinate has an infinite amount of polar coordinates.
Yeah.
But going from a polar coordinate to a Cartesian coordinate,
There's one. Mm-hmm. So going from Cartesian to polar, or polar to Cartesian, we'll talk about the conversion of that. But yeah, since there isn't a unique way to represent the same point in polar, when we express a point from Cartesian to polar, somebody, all of you could have different answers and still be correct. But if we go from a point in polar to a point in Cartesian, all of you would have the same answer. I thought I updated these, sorry.
I'm gonna do it with online classes. Yeah, anything's gonna be an online.
Yeah, no, I think.
Yeah, right. It's like on your desk. Right.
There's not like a lot of debate.
Right.
All right, sorry, I thought I updated your notes. Here's kind of a little bit of what we talked about, the pole here, the origin, polar axis here. But this first one is showing that if we've got a point r theta, then the same point is described by saying r plus or minus 2 pi, theta plus or minus 2 pi rather. So it gives us the same point. And we've got this point r theta, where r is positive. Reflecting that point through the origin equates to negating r. So we can look at things with like a negative r in that way. I'm sorry I didn't have that in your notes.
So say that was like, that number C was like 4 pi over 3, 4 comma pi over 3.
Mhm.
It'd be negative 4 pi over 4.
So sorry, say that again. At this point right here is
4 comma pi over 3.
uh-huh.
The one down there would be negative 4 pi over 3, right?
Negative 4 comma 4 pi over 3.
Yeah.
What do y'all think?
Or is it just that it'd be negative 4 comma pi over 3?
So here, the reflection across the reflection through the origin just has us negating r. This theta and this theta are still the same. So if we think about going out in the positive x direction as a positive r, we could say that this is 4, a radius 4. Or we could go out this way and say that that's negative 4.
Right.
Yeah, and positive, positive thetas rather, we go counterclockwise. Negative thetas, we go counterclockwise. So if we go out negative 4 units this way and then rotate pi over 3 units, we're down here. Which is still pi over 3 from negative 4.
So it's always measuring from the polar axis and.
Yeah, right.
Okay.
Yeah, just like in Cartesian, when we always start at theta equals 0 and then counterclockwise is positive.
Okay.
Yeah, that convention is still true here too. So that's just negating r, we get a reflection through the origin. But let's write out the two ways to represent, two alternative ways to represent a point. one we've seen already with the addition or subtraction of 2 pi. So we'll keep with our point is generic r theta. Okay, one is to take r and add plus or minus 2 pi to theta. That gives us other points. It's the same point, rather different representation. The other way is, start with theta. If we take theta and we add or subtract pi to that, then we simply negate r. So you think about, if you think about any point in that plane being pi units apart, it's on the same line reflected through the origin, right? So if I say, again, that example, if that's the point, I don't know why I drew that, but if this is the point 4 comma pi over 3, when I subtract pi from pi over 3, what do I get? Okay, so I'm going to subtract this. I'm going to get what?
Subtracting that from 3?
Yeah, I'm going to subtract pi from this.
Oh, so negative.
Yeah, so if I look at negative 2 pi over 3, but as an angle here, but keep my radius at 4, I'm going to go out 4 units, and then I'm going to rotate 2 pi over 3. So you can see I'm going to be over here. This is for negative 2 pi over 3, but I want to be over here. So then I just have to rotate this 180 degrees, or the way we're thinking about it with the following figure is I'm just going to take this point and reflect it through the origin. So I'm there, and to reflect it across the origin, I have to make r negative. So then that way, negative 4, negative 2 pi over 3 is this point right here. Same point.
Okay, so what if r is already negative?
If you add or subtract pi to it, you would just make it positive. We've got some examples here. I don't think we have time to look at all of them, but the first thing we want to do is express each point in the above and polar coordinates r theta. And here, let me back up and just state that generally when these things are described, when r and theta are described, typically the r is chosen as positive and the theta is chosen between 0 and 2 pi. It's sort of just like the standard notation for these polar coordinates. So let's state that as well. So usually a point r theta is expressed with r greater than 0 and theta in between 0 and 2. It honestly, like we've said, it doesn't really matter, but that's usually the convention. R is positive, theta between 0 and 2 pi. So let's do that here. Let's do that here for the first part of this problem. We want r to be positive and theta to be between 0 and 2 pi. So maybe we'll look at like 3 of these and then go on to part 2. Okay. I don't know. Let's start with point A. Does everyone have this?
Yeah.
Okay. So point A, 4 comma pi over 6. What do y'all think? 4 comma pi over 6. Okay, so find an alternative representation of 4 comma pi over 6. Okay, so what would negative 4 comma pi over 6 give us? Yeah, across from it. So if all we do is negate r, we get that point reflected through the origin. So if 4 pi over 6 is here, then negative 4 pi over 6 is here. So that's negative 4 pi over 6.
So that's not correct.
It's not correct. Okay, the one I heard was negative 4, 7 pi over 6. Is that right, Richie? What do y'all think? Negative 4, 7 pi over 6. Yeah. So we take, that's the second representation of the point down here. If I take the original point and add pi or subtract pi to theta, then I have to make r negative. So we took pi over 6 and we added pi to that to get 7 pi over 6. We have to then make the radius negative.
Or negative 5 pi over 6.
Yeah. Or we could say it's negative 4, negative 5 pi over 6. Is that what you said?
Yeah.
Yeah.
So then the curve reverts back to that order coordinate. Subtract pi.
Yeah. Yeah, so here, since we subtracted pi, we would add pi to get back to it. But again, if I add pi to theta, I have to negate the radius too. So if I add pi to this right here, I'm back to pi over 6. And then I make negative 4 negative, I'm back to 4 pi over 6, or 4 comma pi over 6.
How do we know?
So how do we know when to subtract and when to add? It doesn't matter. Unless it's explicitly stated in the problem, like represent this point by subtracting pi from it or whatever. If it's not explicitly stated, again, all of you could have in part 2 for A, all of you could have different a different polar point than anyone else. All right, let's do point E. So how do we describe point E in the first part, polar coordinates? 3 comma 5 pi over 6.
It wouldn't be 5 or 6.
Do what?
It wouldn't be 5 or 6.
For E, no, because we're over here. So 3, yeah, 3 pi over 6 would put us here. That's 3 pi over 6.
That's not negative 3.
Well, so we go out 1, 2, 3, and then we rotate by this much. So remember, we wanted r to be positive and theta to be between 0 and 2 pi. Yeah.
Rotating.
Okay, so what's an alternative representation for point E? Negative 3, negative pi over 6. What do y'all think? Negative 3, negative pi over 6. So from the origin, if we go negative 3, we're out here. And then negative rotation, we go clockwise. So here's negative 3. That's negative pi over 6.
You said theta was usually between 0 and 5.
Just for the first like representation. The second one we were just looking at. That's why I put these restrictions here. Granted, they weren't there originally, but we put those restrictions there and not in part 2. Yeah. Yes, the negative pi over 6. Yeah. So if I started here at positive 3 and said negative pi over 6, positive 3, negative pi over 6, I'm good here. The negative 3 at the origin means I go left. Positive is right. So, yeah. No, we're finding, so yeah, maybe there is some confusion here with this statement, but this was just in order to reflect the point through the origin, we just negate r. But notice they're completely different points no matter how you slice it. two totally different points. Okay, how about, let's do point G. What is it? Okay, 4, 5 pi over 3, what do y'all think? For point G. All right, and an alternative representation for G. -4, comma,
Negative pi over three.
-pi over 3, would negative pi over 3 work? So only if the 4 is positive?
Yeah.
If we go out -4, -4, and negative pi over 3 would put us up here, up there. Yeah, we could say it's -4 and 2 pi over 3 to get the G.
Can't you say it's 4? Negative pi over 3.
4, you said 4 and negative pi over 3. So let me write the first one down. And then you said 4 negative pi over 3, Trey?
Yeah.
Okay. Yeah. So what do y'all think about those two as describing point G? All right. I think that's where we're going to leave that. Do y'all have any questions?
So for the rotation, you just keep like the rotation.
When you're, what do you mean?
Cause like, for that last one, we kept going counterclockwise motion, but, or can you just express that also?
Yeah. So if you went out, like if I went out 4, and then I want to describe this point over here, and I go clockwise, then that would just be negative. Whatever. Yeah. If you go clockwise, it's negative. Counterclockwise is positive.
Can we do F?
Yeah, point F. What do y'all think about point F? Say that again. 2, 4 pi over 3. Okay, so for F is 2 comma 4 pi over 3. Valid. Okay. What was that, point F? Yeah. No, so we go out 2, and then our rotation this way is 4 pi over 3. Because this is 3 pi over 3, right? Each tick mark, except for we skip over these middle ones because those are the pi over 4 ones. So 4 pi over 3 when r is positive and theta is between 0 and 2 pi. Alternative representation for F. So say that again, sorry.
-2
-2 comma pi over 3. What do y'all think? -2 pi over 3 for F. So the conversion between each system, or converting one point back to another point. Yeah, let's say we have this point here that's described as x, y. That's our r. We know here dropping a perpendicular. This is our x, this is our y. And this is our theta. So one, or actually two relationships we can get from this is that x is our cosine theta and y is our sine theta. R cosine theta. Let's say x equals what now? Right. So that relationship allows us to convert from polar to Cartesian or rectangular. You should remember that just from a trig class, right? And actually, all the conversions you probably do see in a trig class. I don't know, it's been a while. Okay. I guess the other relationship we have, based on the Pythagorean theorem, we have that x squared plus y squared equals to r squared. And theta, well, let's look at it this way. The tangent of theta is y over x. So in order to get theta, we have the inverse tangent of y over x. Really, this allows us to go from, look at these two. This allows us to go from rectangular to polar. So this gives us our r, that gives us our theta. This gives us our x, that gives us our y.
You can say from Cartesian.
Yeah. So, yeah. Do you have a question, Nelson?
Number one, go from polar to Cartesian.
From this relationship?
Yeah.
Yeah, because you do inverse sine of y over r.
To-
That'd give you theta, right?
To give you theta.
There's a relationship between the two. You have theta.
Yeah, R and
Okay.
theta.
And then you have either r and x or r and y.
So we have let's say we have an r and a theta. What are you asking? Can we use number one to?
Five x. Given like x, you find r.
So if we have like x, this is our polar. If we have x, comma, whatever y is, in the Cartesian, but we don't have the radius, is that what you're asking?
Okay, I guess. Because theta is, I guess, the y.
Yeah. So we would need both here. You need r theta to find both x and y. Here we would need x and y to find r and theta. Yeah, sorry if I didn't quite understand what you're asking. Okay, so here's a couple of examples. As a reminder, what is the output of inverse tangent?
1 over x.
Okay, good. That is the antiderivative. So that is the derivative of inverse tangent. I'm glad you remember that. That's seriously good to remember. But what is the range of the inverse tangent? Yeah, negative pi over 2 to pi over 2. So you just got to be a little bit careful in the situation where, theta is in between pi over 2 and negative pi over 2. which we'll see an example in a minute as to why we've got to make sure that when we convert, especially convert back to rectangular or Cartesian, that we're taking a little bit of care through that. So convert the following point to rectangular coordinates. I don't think our textbook does, but sometimes there's like a P next to the point, so we know that that's a polar. But anyways, we've got a polar point, 1 negative pi over 3, and we want to convert that into rectangular coordinates. So we're given an r and we're given the theta. So we want to describe xy. So x is r cosine theta, and y r sine theta. So that's going to give us our xy coordinate 1/2 for x, negative root 3 over 2 for y. Do I? Oh yeah, sine of negative pi over 3 is y is negative.
Cosine of pi over 3 is 1/2. So it's
Yes.
negative 1/2, right?
No, because cosine is also positive in the fourth quadrant. Or x is positive. So here's negative pi over 3. This cosine, think about x coordinate being positive, cosine's positive as well over there.
Would be like x inverse tangent of like pi over 3.
Are you doing this one already?
For another topic.
Oh,
Before we started, I didn't do it before. I tried doing it by finding y, because that's what I tried doing obviously 1 times the inverse tangent of no, 1 times tangent. I got negative root 3. Well, if that's what.
yeah,
do it
because
that way. I don't know if you could do it that way or not.
yeah, no. Okay, then we have the rectangular or the Cartesian point, -4 for root 3. We're going to convert that to polar. So here's our x, here's our y. So we have r defined to be the square root. Let me write it this way. Let's see. R squared defined as x squared plus y squared. With r squared, x squared 16 plus 16 times 3. 34. Yeah, so 16. So we have positive 16 plus 48. 64. So r squared is 64. And again, what that really implies to us is that r is plus or minus 8. Let's just choose r to be positive, theta to be between 0 and 2 pi again. There's not too much of an issue there. Again, the issue comes with when we take the inverse tangent of that, because the inverse tangent is going to output something between negative pi over 2 and pi over 2. So we have theta inverse tangent of y over x. Negative root 3. So what does your calculator give you for inverse tangent of negative root 3? Does it?
I didn't have so as a pi.
1.47.
Yeah.
I can't find
So is it?
negative 1.47.
Yeah,
Yeah.
One point zero four seven.
It's negative 1.4 something something, which is negative, in your calculator convert, negative pi over 3.
Negative.
Oh, never mind.
So here's the thing though, we've got a r that could be plus minus 8, an angle that could be, well, negative pi over 3 is what we get initially, but kind of the other way we're thinking of this is that the tangent of theta is equal to negative root 3. So that happens over here at this point, right? Here's negative root 3. I'm sorry, negative pi over 3. My bad. But in actuality, what else works? Yeah, 2 pi over 3 also works. Because if tangent's negative, sine and cosine are opposite in sign, right? So here, sine and cosine, positive, negative, sine, cosine, positive, negative. Here, positive, here, positive. So then we've got to ask ourselves, if I'm looking at our r of positive or negative 8 and an angle measure that could be negative pi over 3 or 2 pi over 3, which one actually describes this point? So now it's beneficial to think about where that point is in the Cartesian coordinate system. So that's negative 4, whatever 4 root 3 is. So that's where a point is located in space. Oops, sorry, negative 4 times 4 root 3. So we've got some combinations to work with. All we need to do is pick one that describes that point. So would 8 2 pi over 3 work? Right. So either one would work. That's that when we convert to rectangular, we've got to make sure that the polar point that we actually describe, because the inverse tangent's funky, we get 2 radius, right, plus minus. You just got to make sure whichever point you describe, you put them in the right combination of r and theta. Because if we said 8 negative pi over 3, we're describing this point. And that's not the point for negative 4 root 3. Y'all have any questions on that? All right, I think that's a good time for break. The rest of the section really is about what different graphs look like and how they arise. So we're going to look at sort of really briefly some polar equations and their graphs, talk about how we converge back to our Cartesian coordinate system as well, just so we can, if we don't remember what these look like, at least maybe we can remember the conversions and sort of get our bearings that way. But lines through the origin are described as theta equals theta naught. For example, theta equals to pi over 4. So that theta naught is a particular value. The theta is the variable, or the dependent variable. So how would we convert that to the xy coordinate system to determine that that is actually a line through the origin? So we've got to remember what's involved with our conversion from point system to, or one coordinate system to the other. So we'll look at this example and write down the generic instructions in a minute. But if we take the tangent of both sides, What is the tangent of theta? Y over x. Tangent of theta gives us y over x equals to, what's the tangent of pi over 4? 1. So we have y over x equals to 1 multiplied by x, we have y equals x. So the graph of theta equals pi over 4 is the graph of y equals to x. So our conversion, take tangent of both sides. Tangent of theta we write as y over x. Compute the value of tangent theta naught and solve for y. So notice whatever over here we had tangent of pi over 4, that was our theta naught. The tangent of theta naught gives you the slope of that line. That is the slope of your line. So like if we say y equals x in Cartesian, we know that's just that single line. But what if I said theta equals pi over 4 versus theta equals 5 pi over 4? What would we be dealing with? What's the difference? They're both lines through the origin. So where's 5 pi over 4? Yeah, directly across, right? So if I describe the line by theta equals 5 pi over 4, isn't that the same line? You see that sort of non-uniqueness kind of thing happens right there. I guess it doesn't. I guess it does have some limitations. That's what it says. Oh. Okay. So much for that. So those are lines through the origin. Circles centered at the origin are given by r equals r naught. So for example, r equal 4, what do you think that is in polar? Circle radius 4, yeah, centered at the origin. So circles have a very simple equation, and circles centered at the origin have a very simple equation. So how do we convert that into Cartesian? Yeah, so the x squared plus y squared. But before we have that, we have to multiply or square rather both sides, right? So I'm going to square this side, and I'm going to square this side. R squared is x squared plus y squared. So So we have x squared plus y squared equals 16. We had to square that r to get it to be x squared plus y squared. Our conversion is to just square both sides. And write r squared as x squared plus y squared. Easy enough? So the circle shifted either horizontally or vertically, but not both. There is a way to describe a circle centered where it's shifted horizontal and vertical, but we're not going to deal with any of those. So a circle shifted up or down is r equals 2a times sine theta. Shift left, right, r equals 2 cosine a, 2a cosine theta, sorry. Yeah, I'm going to put something else in your notes. Sorry. Let's look at an example of that. So let's take, for example, r is equal to 8 sine theta. So how would we translate that back to xy?
Y is being shifted
Yeah, your y is shifted of the center. So notice we don't have anything that's familiar to convert, right? We don't have r squared equals this. We don't have r sine theta to turn that into a y. So that's a hint. So if we divide by 8, we still need x and y in here. With sine, we need an r sine to turn that into a y. With the r, we need an r squared to turn that into an x squared and a y squared. So if we solve for theta, that wouldn't give us anything as far as x and y are concerned.
What's the a in the equations number where it says 2a sine theta?
Yeah.
Do we need to divide 8 by 2 to get an a value that means something?
No, so we'll not divide, but we need to think about this as 2 times 4 sine theta. And so a is 4. So if we need an r squared over here and we need an r sine theta to convert, notice I can't just square it because then I'll have r squared. That's fine. I want r squared. But then I'll have 64 sine squared theta. Instead of squaring both sides, what happens if I take and just multiply both sides by r? So now the left-hand side becomes x squared plus y squared. And the right-hand side is 8r sine, which is 8y. So now what we're looking at is x squared plus y squared minus 8y equals 0. And then we complete the square with y to get that into the form of a circle. We subtract 8y, but it's 8r sine theta, so that's 8 times y. R sine theta is y. So we have plus y squared minus 8y. Half of 8 is negative 4 squared is 16. Completes the square. So we have x squared plus the quantity y minus 4 squared now we see that it's a circle. Whose center is at 0, 4, and whose radius is 4. And so going back up to the top, we see that a circle that's shifted up or down is described as r equals 2 times a sine theta. Where we were originally talking about 8 sine theta, we viewed that as 2 times 4 sine theta with our a equal to 4. So we have a circle shifted up 4 units with a radius of 4. Shifted up a units with a radius of a. Does anyone have any questions on that?
So why did splitting 8 into 4?
Well, because based on the nature of when we complete the square and stuff, we get that this is a circle of radius 4 with a center of 0, 4. But
So
if,
we really didn't need to do that.
well, I mean, if you look at this and say it's a circle centered at 0, 8 with a radius of 8, that's wrong, right? So we're just kind of fitting the Cartesian equation, circle radius 4, center 0, 4, with this right here. So that a determines both the radius of the circle and the center, but it's that number times 2, a times 2. Or if you want to think about it, it's whatever number is attached to sine divided by 2. That describes where your center and your radius.
So you can just verify.
Yeah.
And that's all verified.
Yeah. It's always the case. So conversion. Multiply both sides by r. And then write r squared as x squared plus y squared. And depending on which one you're dealing with, of course, we would have x equals r cosine theta. We would rewrite r cosine theta as x, or like we did here, r sine theta as y. And then we complete the square. Do you have any questions? So what if I had r equals to 22 cosine theta?
We shifted
11 to the right. Yeah. So cosine is associated with x. This is a circle with radius of what?
X minus 11 squared.
Radius 11, centered at 0, 11, we would move it up 11.
The 11,
11, 0.
And the formula would be what? X minus 11 squared plus y squared equals what?
Yeah, x minus 11 squared plus y squared equals to 121.
100.
So you could, like, if that were in negative 22, let's say, you could go through the same process and you would find that the radius is still 11 because we're squaring these things.
How do you complete the square? Like, how do you know to add 16?
Oh, so the process to complete the square, you take half of the, half of the b term, which is,
Square, right?
yeah, and then square it. That's what you add to both sides. So that's not, I don't see that in your textbook anymore.
Or, if you take half of 11, it's square. It's just
Well, yeah, it would be 22. Because we would multiply both sides by r. We'd have r squared equals 22r cosine, or x squared plus y squared equals to 22 times x.
But probably this is a question. So, if we wanted to, like, if it was shifted left or in the y direction, we shift down, you could throw a negative. There would be a negative in front of these.
Right. Yeah, and that's what I was looking for. They don't. The older editions seem to have that. It might be in the summary somewhere, but let me just write this out then. The equation r equals a is a circle of radius absolute value of a centered at 0, 0. R equals to 2 times a sine theta is a circle centered at 0, a with a radius, again, absolute value of a. And 2a cosine theta. Center a 0, radius absolute value of a. Centered at a 0. For the bottom one. So we can describe circles that are, centered off the x and the y axis, but we don't encounter those. So it doesn't look like a circle, it's kind of an optical illusion. No, it looks like a circle. This off-center here, center is at 2, 4. But anyways, that is possible. We can describe horizontal lines as r sine theta equals to some number. For example, r sine theta equals to 5. It's just r sine theta is y. That's y equals 5. There's really much conversion to describe here. Vertical lines, x equals to cosine, r cosine theta equals to b is a vertical line. So that's x equal to b. So there's two types of spirals. I didn't list the other one. It is actually in your homework, so I'll mention it. But spirals take the equation r equals theta. For these, if you have to determine what they look like, just graph in Desmos. Really, we just want to know what lines and circles look like. kind of have a familiar sense of other things, but I won't require you to graph those on the test or solve problems by finding the graph first, unless it's just a circle or a line or something. So this is, I really don't know how to spell Archimedean, but this actually gives you an Archimedean spiral. Oh, is it?
Oh, wait, no, I guess.
Yeah, no trademarks or copyrights. Yeah, it's probably total. This is an Archimedean spiral, the logarithmic spiral. The logarithmic spiral is e to the e to the 8 theta. R equals e to the 8 theta. So the thing with Archimedean spirals is they have it's equal spacing between each consecutive ring, I guess. And logarithmic spirals, it's more of this exponential growth between the spirals. We'll look at a couple, but there's really not a lot we do with those. So there's our R equals theta. R equals 5.5 theta. Yeah, those are logarithmic. Yeah, the golden spiral is a logarithmic spiral. So I don't know, maybe you can see it's sometimes it's subtle, but the difference between, see how this is kind of spiraling out exponentially, whereas the Archimedean spiral, make that a little tighter. The Archimedean spiral is equal spacing between. So yeah, this one is our some variant of it is our golden spiral, Fibonacci spiral. Okay, we do see a lot of graphs that deal with cardioids, but again, you're not responsible for graphing these. So like in your homework, if it says graph this cardioid, then just again we're using Desmos. So notice we've got a cardioid R equals A plus B cosine theta or A plus B sine theta. Cardioid is generated when the magnitude of A and B are the same. So I'll just take a few from here and put those in our notes. So we'll do 3 plus 3 cosine theta. So there's a cardioid. Yeah. Yeah, you can look on like MathWorld has if you look up cardioids on MathWorld, or Wolfram MathWorld, whatever it is now, they do have a lot better like heart shapes.
So what if it was like 3 plus 4 cosine?
So then we'll get the shape below that's a renaissance. I don't know. To me, that doesn't look like a heart. I don't know who named it, but yeah, peach is a little better. I think more appropriate. I'm just trying to get that. Trying to fit a square on a circle. Ancient problem. We create a square whose perimeter is equal to that of the circle is.
Got really close.
Yeah. You can do it. You can't do it with a compass and a straight edge, though. But you can do this. Okay, and then how about 2 plus 2 sine theta? We'll do 3 plus 3 sine theta. You see Yeah. The orientation changes. Now sort of that cusp is kind of pointing in the y direction because we're dealing with sine, whereas the cusp with cosine, it's pointing in the x direction. And then typically how we see these in practice is it says find the area of this cardioid or something like that. So let's write our equations here. Okay, so those are cardioids when A and B are the same. When A and B aren't the same, you've got a couple of scenarios. This word is, there's actually, I don't know what the name for it, but have y'all seen like that little squiggle under the C before? I have no idea what that's called, nor what language that corresponds to, but
It's like acai.
yeah, yeah. So this is pronounced limason. I don't know how you say it. Phonetically, that's whatever. And again, these are, you're not responsible for these either. This is another Desmos thing. If anything is required from any of these other shapes that we've got Desmos next to, like the graph will accompany that on the exam. But for your homework, you might just need to graph it. Okay, so we'll look at two of those. 1 minus 2 cosine theta. Yeah, when A and B aren't equal. So we've got our inner loop here. Yeah, these are a little harder to graph. So 1 minus 2 cosine theta, and then we'll look at one that doesn't have a loop. So let's look at 1.5 plus 2 sine of theta.
Also, it's like a little overlap.
That's a little more subtle to do. So that's even more subtle. It's not a perfect circle, but it kind of looks like it. It's kind of like cardioids are like special cases of these. But it's, I don't have to. Same thing.
Oh, we have to. This could be like our test.
I wouldn't use on the test. Because I mean, you notice when you look at, especially the ones with the inner loop, you know, that's hard to graph because what you're getting here at maybe at the pole end when theta is pi, you've got at least two different points generated. Right? So like if you looked on the graph, if you were just plotting points, you would end up with something like this. Well, I have a point here, I have a point here, and I have a point here. Maybe you found this point, and that's it, right? So you have like these 3 points. It's really hard to tell. Then you've got to plot all of these other points here, here, whatever. Then you got to get a whole lot of points. So just due to the time-consuming nature of that, it's not practical for an exam. So like for your homework would say, this is graph 2 plus 3 sine theta equals r. And really, I hope you know that that's not a cardioid because those two numbers aren't the same in magnitude. So this is where you just go online and graph. 2 plus 3 sine theta. So there we go. So there are a few in your homework that you can use that to do. Okay, the last one is also similar to one of the homework problems. Well, maybe we've got a couple more, but this one's similar to a homework problem. It's not that straightforward, I don't think. But we want to convert r sine theta equals to 8 sine of 2 theta. So the first thing here is to change sine of 2 theta into that, or use the identity. Sine 2 theta is what?
1 plus
2 sine cosine. So we want to write that as 2 times sine theta cosine theta times r8. So we have r sine theta equals to 16 sine cosine theta. It's not really that obvious, which is why I just wanted to talk about it briefly. There's really two things that can happen. One, I could say that r is 16 cosine theta if I divide out the signs, right? But if I divide out the signs, then what that implies is that the sine of theta is not 0. So in order to divide through by that, it has to be a non-zero thing. So r equals 16 cosine theta, what is that? It's a circle. Radius 8. Centered at 8, 0, right? So that's 2 times 8 cosine theta. Circle. Center at 8, 0. With a radius of 8. If sine is not 0.
You have like an r equals negative 16 cosine theta, would you end up with that center at negative 8, 0?
Negative, because remember our center is at a 0, and if that is negative, that 2 is always positive in that formula. So then, if we had a negative 8 here, center negative 8, 0, radius is still 8. The other thing is, if we said if sine is not 0, we could divide through by sine. But what if sine is 0? Then we can't divide through by sine and get that equation of a circle anymore.
So that would just be r sine theta equals 0, right?
So I think the most advantageous way to think about this is if sine is 0, then 16 sine cosine is 0. So r sine theta equals 0. What is that? Y equals to 0, right? This is y equals 0. and y equals 0 is the x-axis. So that equation describes a circle centered 8, 0, radius 8, and the y-axis.
Are you saying that it can describe either one of those, or describes both of them?
Both of them simultaneously.
Oh, so it's-
Well, it depends on what sign is.
Oh.
So if as long as sign is 0, we have the x-axis. Any other values of theta that don't make sign 0 will give us a circle.
So hold on, so if sign theta was 0, wouldn't that be r times 0?
Yeah, which means that, so if that's r times 0, then that means that it's kind of able to be whatever it wants, right? It's anything times 0. I don't know, there's something that still bugs me about that problem. Just a couple more examples. Convert. So let's look at r equals to cotangent theta times cosecant theta. Just so we can see that, you know, if other trig functions are also in there, it's still a legitimate polar graph. So what might we want to do to convert that into xy? Yeah. So we want to rewrite these as sine and cosines, or combinations thereof. So we have cosine theta over sine theta times 1 over sine theta. Then what would we do?
Theta over sine squared.
So yeah, so what would we do with the sine squared?
Make that an identity. So it'd be 1 minus sine squared.
So, okay, so if we change sine squared into an identity, 1 minus cosine squared, what would that do for us? So what would this being equal to r do for us?
Well, if we multiply it,
Yeah.
it'd be r.
So here we would say it's from here, Andrew, is that?
Yeah, cosine theta equals 1 minus cosine squared theta times r.
Okay.
And then you'd be able to subtract or have it equal to r equals
X over 1 minus cosine squared theta.
R minus r cosine squared theta. When we convert from polar to rectangular, does having a sine squared or a cosine squared in there help us?
That's not saying cosine.
So, you know, like you're correct. This is r minus r cosine theta, cosine squared theta.
What you just put that cosine on the other side?
You could then factor it. So if we looked at it as cosine theta equals r minus r cosine theta times cosine theta, I think that's a little bit closer to helping us, right? Because we know that this r cosine theta is x. This r is just r. This cosine is still cosine. So what if we then multiply both sides by r? Right, so we have r cosine theta, this is x, this is r squared, so that's x squared plus y squared. We have minus r cosine times r cosine. So we have minus x squared minus x squared, so we get x equals y squared. So that's kind of the trick. If you see there, if there's already r's present with some things and not other things, then multiply through by r will give you the r with cosines or sines and an r squared. I guess if that's kind of where you're headed. From here, we could also do that. We could say, we could multiply both sides by sine squared. Break this up. This is r sine theta times sine theta equals to cosine theta. And then from here, multiply both sides by r. So from here, we have y times y, which is y squared, equals to r cosine theta, which is x. So however you go, you should end up with y equals to x squared, which is a parabola opening to the right, centered at the origin, or vertex at the origin.
Put it as y equals negative x.
Yeah, well, yeah, be careful though, because it would be y equals plus minus square root of x. So you'd get that square root curve and then a negative square root curve. Okay, last one. Let's say we have r equals 1 over 2 cosine theta plus 3 sine theta. What would we do there? No, partial fractions would work if we had like the product of stuff on the bottom there. Yeah. So we're just like we do with when we always have fractions. So does that work for us? Once we distribute the r, right, we have 2r cosine theta plus 3r sine theta equals 1, which means we've got 2x plus 3y equals 1, which is our line, slope-intercept minus 2/3 x plus 1/3. So we do have ways to also describe lines that don't pass through the origin. We don't do a lot with those either, just FYI. Does anyone have any questions on 12.2? So 12.2 is more like to get your bearings for 12.3, because in 12.3 is where we start looking at derivatives in areas and arc lengths and stuff like that. So really the key to this, to when we're doing like calculus with polar coordinates, is to think of polar coordinates as a parametric equation. That was 12.1, with the parameter being theta. So here what we're dealing with is r is a function of theta, which is weird because we write r theta as the point. We're typically when we do that, we write a point, we write out the independent variable and the dependent variable. But when we look at a point that's r theta, really theta is the independent variable here. That's our parameter, more or less. So it is a little backwards, but we do want to think about it as a parametric equation with parameter theta. And so the derivative in any coordinate system, as we saw in 12.1, the derivative in any coordinate system is the rate of change of the vertical coordinate with respect to the horizontal coordinate. And that took a slight variation in 12.1 because we had a parameter t, it was dy over dt. That's the vertical change, divided by dx over dt would be the horizontal change. Dy over dx kind of thing. Let's see what's here. I realize I don't have the formula for the derivative, but I want to show that here. As a reminder, like I just said, from 12.1, we had the derivative of y with respect to x was the derivative of y with respect to t over the derivative of x with respect to t. So here in 12.3, when we're talking about the polar, r equals to f of theta, we have that the derivative of y over, or with respect to x rather, dy over dx. We're going to look at that as the derivative of y with respect to theta, there's our parameter, over the derivative of x with respect to theta. Okay, so that's what we're looking at. And then we're about to make sense out of that. So we're going to parameterize polar equation from 12.2, where we had x equals to r cosine theta and y equal to r sine theta. So there's x represented as our parameter theta and y as our parameter theta. Since r is some function of theta, we're going to rewrite x as r cosine theta. We're going to call that f of theta times cosine theta instead. So now x is completely in terms of our parameter theta. We do the same thing for y. No, because r is some function of theta. It's going to be the same thing. Because when we're given a polar curve, it says find the derivative of like r equals to 2 cosine theta. So that's the same function, the same r for both of our x and y coordinates. So to take the derivative, now that we've parameterized it in terms of our parameter theta, here's our derivative. We just have to take the derivative of y with respect to theta and divide that by the derivative of x with respect to theta. So this is, in terms of theta, the product rule is what we're using here. So we have x prime, or the derivative of x with respect to theta, is the first times the derivative of the second. So that's negative f of theta sine theta times the second time derivative of the first. That's f prime of theta cosine theta. Is everyone all right with that? Just product rule with respect to theta. Same thing for y prime, or dy over d theta. You got the first times the derivative of the second, plus the second times the derivative of the first. I'm sorry I didn't have the formula, but we have it here. Thus, the derivative with of y with respect to x is, we can call that y prime over x prime, as long as we know that we're talking about the derivative of y with respect to theta and the derivative of x with respect to theta. So the derivative of y, we have that's f of theta cosine theta plus f prime of theta sine theta all over the derivative of x, f prime theta cosine theta minus f of theta sine theta. Unfortunately, that's as easy as the derivative in polar coordinates gets. If you just remember to reparameterize like we did up there, you don't have to remember that formula, because the derivative is just derivative of y over the derivative of x. And when you write out the function, you'll see that it's a product. Maybe it's not a product, but so you don't have to remember the formula. If you want to remember it, you can. The idea is when we were asked to find the derivative at a given point, we have this r, which is that f of theta. All we have to do is remember to reparameterize things. Since y is r sine theta, y is f of theta times sine theta, and given f of theta here is this r, so y equals to r times sine of theta, or f of theta times sine theta. Is everyone okay with what we've done there? If you just want to remember the formula, feel free. You don't have to go through this process. But now we have y as a product. Take the derivative of y with respect to theta with the product rule. Or we could just say y is the sine of theta minus sine squared of theta. And then we can just use derivative of sine squared. However you want to look at y. Either or. And then we parameterize x the same way. X is f of theta times cosine theta. So it's 1 minus sine theta times cosine theta. So our f of theta is r. And so x is cosine minus sine cosine. We will have to continue here on Tuesday. I think at this point we just need to look at the examples that are relevant to the final. Please start thinking about your note card, no chapter 12 stuff on your note card, no worked examples. But probably want to start constructing your note card if you're going to use one, and reviewing old exams. I think probably one of the best ways initially to study for the final is to just print off the blank exams, take those blindly, and then look at the keys to see what you missed, and then that way you know what areas to focus on.
Are you gonna make one of those keys that you made every time?
Yeah, I'll do that, because I'm actually going to write the final this weekend.
So you can make that, you'll make that this weekend.
I can try.
I'm not trying to make you, I was just wondering.
Yeah, I can't make any promises.
You have a life, like, please live your life.
Definitely on Tuesday we'll talk about it.
I'm a really low tech person.
I know, I
My
know.
laptop, right?
You just figured it out, and it like went right away.
I think you can tell Word, like, you can type it all out on Word and just tell Word to print 3x5.
Oh, really?
I think so.
Yeah.
Yeah.
Very, very.
Talk to me.
Very, very basic. It's been so long.
This I guess, too.
So when it came to this, always gets me confused. So you go through this, and it's like, you know, I wanna find one, there's like issues around. Is there an order of operations to do it?
Oh, I see. So you isolate the thing that you're solving for, so regulations. Isolate that. You have to subtract that. It's attached by addition. You subtract that. Okay, so then I have 3y minus 2x plus 1.
And then you divide by. Alright, so that's the order, you wanna get it by itself, and then detach anything that's attached by
Yes.
multiplication.
Yeah.
Alright.
If it's attached by multiplication.
Get simple rules.
Yeah. Yeah. And I think